Hello again. We're going through some dynamics problems, and the next two that they've given us have to do with free body diagrams, where we're drawing force arrows to show all the forces acting on something. And they start us with a stationary block on a horizontal surface. So think of this like a brick sitting on a table. Well, assuming this table's on Earth, gravity's pulling down on the brick, so the first force that we kind of automatically have is gravitational force pulling down. Gravity always pulls straight down towards the center of the Earth, so the direction's easy there. And if you're sitting on a table and the table's holding you up, that means the table is pushing up on you to support your weight. That's what we call the normal force. And it's always at right angles to the surface. Most tables are flat so that their normal force is straight up. And those two forces cancel each other. When you draw a free body diagram, you are supposed to make an effort to make the sizes of your arrows correspond to the sizes of the forces that they're talking about. So, and I'm not very careful about that, I admit, but if we're doing this right, because these forces are equal, we should have equal sized arrows on either side. That way, at a glance, you can see those forces are about the same. They're probably canceling each other. Now here, they switch to an object that's moving, but it's moving at a constant velocity. And constant velocity means your acceleration is zero. And if your acceleration is zero, then F equals ma tells me that your force must be zero. The net force on this object has to be zero, and that means all the forces on you are canceling out. So it's very tempting to think if you're moving, there must be forces on you. Not necessarily. If you're cruising along at a steady speed, that means all the forces on you have canceled. So with this block also, we should find that all of the forces cancel each other out. Those forces are going to be, again, gravity pulls down, always. If this is a toboggan or something, then we have a normal force from the ground or the snow pushing up in the opposite direction, so those two forces cancel. That's why we aren't sinking into the ground or floating up into the air. And at the same time, we have an applied force to the right. This is a person pulling the toboggan or whatever, something that's keeping this object moving to the right. And over on the other side, we have friction. Friction always goes against the direction an object's trying to move. And again, because it's constant velocity, I know these two forces have to cancel, and so I tried to draw the arrows equally sized to show that the friction is this strong and you're pulling exactly hard enough to cancel out the friction so the object just keeps moving at a steady speed. If you were trying to pick up speed, if there's a kid on the toboggan yelling faster, faster, then you would increase this force so that you beat the friction and get the object accelerating. But if you just want to cruise at a steady speed, then you want these forces to match. And if you want to let the toboggan stop, you just slack off on your force, let this arrow get smaller. The friction force will drag backwards until it stops the toboggan, and once it's stopped, the friction doesn't have a direction anymore. It just stops existing, and the object will sit still until somebody comes along and moves it again. Fair enough. What else have they got for us here? A 4-kilogram mass is subjected to a 60 Newton east force and accelerates 10 meters per second squared east. What is the friction? Okay, so this is like our toboggan, only they're giving us numbers instead of just making us draw the arrows. So we have a thing, and it's 4 kilograms. You don't have to put that in the object, but I kind of like to. Someone's pulling it 60 newtons to the east, and its acceleration is 10, and they want to know what the friction is. So there's a friction force, FF, force of friction, but we don't know how much. And we have Newton's second law to help us, which says the net force on this object equals mass times acceleration. Now, let me just mention quickly, if we were doing every single force on this object, we would have to draw gravity pulling down and the normal force from the ground pushing up, canceling it out. But unless we're sinking into the ground or something strange is happening, these forces always cancel out. So I'm not interested in tracking those. I'm going to ignore them. Everything here, the force and the acceleration, are all to the east, so it's the horizontal motion that really interests us. I'm just going to blow off those two forces and not calculate them. I totally could, but it won't do us any good, so eh. So, F net equals ma is the standard form of Newton's second law. Our net force is made up of two: the applied force and the friction force. I'm going to say F applied plus F friction equals ma. The applied force is 60 newtons, and like we normally do in math, I'm going to say that to the right is the positive direction and to the left is the negative direction. So this applied force gets called positive 60. And then we have a friction force. I don't know what it is. I know it's going to be negative, but I'm not going to do anything to make that happen. The math will give me that negative sign. For now, I'm just saying, pretend you don't know anything about this force. Just put a plus on it. It'll come out okay. The mass of the object is 4 kilograms. Its acceleration is 10. So now we have 60 plus F equals 40. If you want to solve for FF, subtract 60 from each side, and you get FF equals negative 20. So the friction force is 20 newtons, and the fact that it came out negative tells us it's in the negative direction, which is to the left or to the west. So you can write 20 newtons west, or if you write negative 20 newtons, because of our sign convention, that does the same thing.